Hey guys, now that you've taken exam 1 and you've learned a little something about the normal model, its properties, how to get probabilities, percentages, and proportions from it, we're going to move on to the next section and focus on probabilities. But before we can talk about the properties of probabilities, we really have to set up the language of what we are talking about when we're talking about different outcomes and different events of probabilities. So when we're dealing with a probability, what we're dealing with is a random phenomenon. So a random phenomenon is a situation in which we don't know what's going to happen, but we do know what the particular outcomes might be. So for example, in a coin flip, that's a random phenomenon because we don't know how the coin is going to land, but we do know the possible outcomes. The other definitions then are the trial, the outcome, the event, and the sample space. So the trial is just one occurrence of a random phenomenon. The outcome is just that particular value that random phenomenon holds. The event is any combinations of these outcomes, and I'll go through some examples of each of these different definitions. And then the sample space is just all possible outcomes. So for example, with a coin flip, the sample space is heads and tails because that's the only two events that could possibly happen with a coin flip. So let's look at a few examples. With the coin flip, for example, one trial would just be one flip of the coin. And so the outcome is either going to be heads or tails. There aren't a lot of other events that are possible. You're either going to get a heads or you're going to get a tails. And so the entire sample space is the collection of all possible outcomes. We would just simply write that as H or T to represent each possible outcome. The rolling of a die is also a really good example of a random phenomenon. A die roll has 6 different outcomes. It could come 1, 2, 3, 4, 5, or 6. One trial is just going to be one roll of the die. And so an event, you could have different combinations of outcomes. So you might think of the event of getting an even number. There's different ways that you could get an even number. You could get a 2, a 4, or a 6. And so we would write that as this. So there's multiple ways for that event of getting an even number to occur. The entire sample space is going to be all possible outcomes then, and you can see how that's written here at the bottom. Why this is important, how we write it, is we're going to use this information later in calculating our probabilities. Now let me go through one more example of a random phenomenon, something that you might not exactly think of as a random phenomenon. Let's think about the price of gas. So you're going to go get gas from the gas station. You're going to choose one in town. That would be one trial. Now you don't know exactly what they charge, but you do sort of know there's a range of values. The lowest price they probably charge is a penny. The most, they can charge up to $1 million or maybe even more. So anywhere in that range, between a penny and $1 million, that's the possible price of gas. Now you're hoping that it's between $2 and $3. That would be an event because there's a bunch of different outcomes. They could charge $2.01, they could charge $2.02, they could charge $2.50, they could charge $2.99. Any of those possible outcomes would fall in the event of being between $2 and $3. The sample space then would be all possible outcomes, so they could charge anything between $0 and up to $1 million or even more, so this could probably potentially go up to infinity. So now that we've discussed how to talk about a random phenomenon, its event, outcome, and sample space, let's try a few problems. This first problem asks, how would you write the sample space for recording the order of heads and tails when you toss the coin 3 times? So one outcome is tossing the coin 3 times. So one possible outcome would be just getting 3 heads. So you can see this sample space looks a little bit different than one coin flip because we have to notate all 3 potential outcomes of 3 coin flips. So you could have 3 heads or you could have 3 tails. You could have 2 heads and a tails, but you could also have 2 heads and the tails in different combinations. And so there's a lot of possible outcomes when you flip a coin 3 times. So you can see that when I write out all possible combinations of flipping a coin 3 times and getting either a heads or a tails, you can see that there's 8 possible outcomes when I write out that entire sample space. Let's try another problem. In this problem, we're looking at a family that has 5 children. Now, we don't know how many boys that they have, but we can write the sample space for how many boys we think they might have. So they could have 0 boys. It could just be a family of all girls, or they could have 1, 2, 3, or 4, or even 5 boys in their family. They couldn't have 6, obviously, because they only have 5 children. So this is how you would write the sample space for the number of boys in the family if you don't know in advance how many boys they have in the family. So you could think of this as a random phenomenon. Let's try a sports problem. Maybe this will be a little bit closer to home. When you shoot a basketball during a basketball game, that's a random phenomenon. You don't know if you're going to make it or not, and you don't even know if you're shooting a 2-point or a 3-pointer or a free throw. All of those are worth different values. So the sample space here that we're looking for is the possible number of points awarded. So if they miss the shot, it's going to be 0. If they make it, it could be a free throw, they would get 1 point. If it's just a regular shot, they get 2. Or if it's past the 3-point line, they would get 3 points. But you're never penalized for shooting in basketball, so there's no negative numbers in this sample space, but you can never make more than 3 when you shoot the basket. So why is this important? Well, we're going to use these sample spaces and possible events and outcomes when we create what's called the long-run relative frequency probability. So this formula here gives you an idea of how you might calculate the probability of an event, let's say an event A. When we talked before, we talked about an event from a die roll that lets you look at an event A that might be getting an even number. And there are 3 different ways that you could get an even number. But there are also 6 different ways or 6 different possible outcomes when you roll a die. So those possible outcomes are the numbers 1 through 6, and that's our entire sample space. So the probability that you would get an even number would just be 3 over 6. And that's how you calculate the long-run relative frequency probability of getting an even number from a die roll. Now, the reason why it's calculated this way is because of the law of large numbers. And the law of large numbers basically says that the more you do repeated independent events, the closer you are going to get to that long-run relative frequency probability. And so that relative frequency probability is the true probability in the long run of an event happening. Now, the important concept here is that the events have to be independent of one another. So what independence means is that the outcome of one trial doesn't influence the outcome of another trial. So coin flips are independent events because if you get a heads once, it's not going to affect the probability that you get a heads on the next flip. The same thing for the die roll. All die rolls are independent as long as you're dealing with a fair die. However, our example of the gas stations with the price of gasoline, those probably aren't independent. So if you go to one gas station in town, the gas station across the street probably bases its prices off of its competitors. So in that example, those wouldn't be independent events, and we couldn't use the law of large numbers for our probability calculations then. So it's important to note that you need to be dealing with independent events, because if you're dealing with dependent events and calculate relative frequency probabilities when the events are dependent, you'll end up with biased estimates again, or biased probabilities. So to start our analysis, we're going to assume that we're dealing with independent events, and then we're going to complicate the models a little bit by then looking at how do we correct the probabilities when we're dealing with dependent events. So that's it for this video. In the next video, I'm going to show you the rules for probabilities and how you can add and multiply them when it's appropriate and when it's not appropriate.